All right, let's take a look at Newton's second law for rotations. Okay, we saw previously that if we had a force acting at some distance r like this, that we could take the perpendicular component and find the definition that the torque is equal to that perpendicular component times r, or we could say r perpendicular times f. We didn't look at the effect of this, though. This would be the cause, right? We have some force acting at a distance. Well, that causes a rotation, but it doesn't cause just a rotation. It causes an angular acceleration. It causes some alpha. So, we have a torque. We can say that we're going to have some change in angular acceleration, or change in angular velocity, due to some angular acceleration alpha. Okay, so how can we derive this? Well, if we have good old Newton's second law, force is equal to mass times acceleration, and we're really just looking at the tangential components here, so we'll subscript these with a t. We also have our torque definition right here. And let's rearrange the torque is equal to force times r. We can say that the force is mass times acceleration, right? So that gives me this new definition for torque. And remember, we have, if we have a alpha, some angular acceleration, then that gave us some tangential component, right? A wheel spinning with some alpha has some tangential component of acceleration. And we said that acceleration was equal to alpha r. Well, we can substitute that in for the acceleration, and we get that the torque is equal to nr squared times alpha. Now you might recognize this, I hope you do, as the moment of inertia I. So what this says is that a torque causes the moment of inertia, or causes the object with some moment of inertia I to accelerate with some angular acceleration alpha. Once again, we always do this in radians, and this works for as many forces as we want. So we can say the summation of the torques equals the summation equals the I alpha for that body. And there's a vector definition of this. We will get to that. But for now, if we, let's say we have some object like this, and there's a force here, a force here, and a force here. Well, first thing we should do, if we know that it's bound to rotate about some point, is find those perpendicular distances. So it'll be d1 for f1, and this one looks like the perpendicular distance would be something like this. And this one I would project through, draw my perpendicular like that. So we'll go d3. So each one of those forces, F1, F2, and F3, are contributing a torque, causing this to want to rotate. Now we know that if we can calculate I, the moment of inertia for this blob or this mass, that we can figure out how fast it'll start spinning, what kind of value it will have for its angular acceleration. So this is when we go back to either integrating to get our moment of inertia. So we can say the moment of inertia is the integral of r squared dm. But pretty much go to the table. Every physics book, every dynamics book, very easily found with a Google search, will give you the moment of inertia table. And that'll tell you what value I you should be using for what axis of rotation. And I wanted to go over one thing about I real quick. The moment of inertia. Pick up your pencil and rotate it about the center. Pick up a dumbbell, pick up something that's like long, skinny, and has an even mass distribution, right? And rotate it through the center right here. Like literally do it right now. I'm doing it right now. And then hold it by the tip over here at the eraser or something, and try to rotate it back and forth now. It's much more difficult to cause it to rotate about the end than it is from the center. And the easiest way to rotate it would be about this center line right there. And so you get that from the tables. We could rotate this through that axis there also. We could rotate it about any point. That is all found in the table, and if not, then you can go back and integrate to get it if you need to. Okay.